Okay, in this video, we're going through assignment number 2, which was a review on states of matter and phase diagrams. Complete the following sections about each of the states and then about a phase diagram. This will be worth 10 points of classwork. Be sure to complete each part to receive full credit. So, section number 1 was solids. You have 5 minutes to work on the first 3. If you finish early, you can keep working through it. After 5 minutes, we'll review them. So our first thing was draw what solid particles would look like and give two properties of a solid according to KMT. So remember KMT is just that kinetic molecular theory. So if we're drawing our particles, remember we're going to draw them as circles as we're going through. And remember that they're going to be in a fixed position and close together because they have the strongest IMF out of all of our states of matter. Now, if we're talking about properties, we're going to see that they have definite shape, they have definite volume, we're going to see that they're in fixed positions. Now yours only said to write 2, but I'm going to write a few, and you might want to write it down on your paper too. They also vibrate in place. So those are just a few properties of our solid for it. Now, which one of the following would be an example of an amorphous solid? Explain why you chose that letter to receive full credit. So we have A, B, and C. And if we take a look at A and B, what we see is that a uniform shape. So we could see that A is a crystal. We can also see that B is organized, repeating. It's a crystal too. But what's happening with C? So we have like a kidney bean shape, we have a weird side shape, it's all over the place. So C would be amorphous because it is disorderly and it has no pattern. So that's a key feature about an amorphous solid is that it lacks order, unlike what we have for our crystal there. Some examples were plastic, rubber, or glass. Now, does freezing gain or lose, so we have to choose one or the other, energy when it goes from a liquid to a solid? So if we imagine that we have a cup, we have our liquid particles within it, and then we're going to make it into ice, a solid part of it. So is it going to gain energy, meaning that it takes in energy, or does it have to lose energy to become more rigid? So hopefully you chose that it would need to lose energy to make this transition for freezing. So then the alternative, melting, would be gaining energy. Okay, section number 2, moving on, we're now going to talk about liquids. So draw what liquid particles would look like and give two properties of a liquid according to that kinetic molecular theory. So if we're drawing our liquid particles, we're going to draw them on the bottom. They are more spread out than our solid, and they have the ability to slide past one another. So I'm going to kind of try to draw it like it's 3D going in with one another, and then you can see them all around our shape. So we would say that it has definite volume, but it has in-depth shape. That just means that it takes the shape of whatever container it has for it. We're going to see that the particles have the ability to slide past one another. So according to kinetic molecular theory, they're still all moving for it. And these are going to have weaker IMF forces, but it would also be denser than what we see for gases. Okay, for liquids, when boiling occurs, what happens to the temperature of the liquid? So as we're going up, we're gaining energy from our burner right here. But once we start boiling, we're going to see that the temperature is actually constant. It would remain, if this is water, around 100 degrees Celsius while it boils. So while it's boiling, it's at a constant temperature. If we were looking at a graph, we would see it as a straight line for it. Now, the final question, as altitude increases, so as we're going up our mountain, we're increasing, the pressure of our gas molecules are decreasing. What's going to happen to our water that we're boiling? Would the boiling point be higher or lower. So if we remember, we have our pot right here, we have our vapor pressure, aka the pressure above our liquid right here. Then we have our external pressure on the outside. As we increase our elevation, our pressure goes down, so we have a lower pressure around it. That means that the vapor pressure has less to get to be equal, aka to boil for it. So we would see that it would have a lower BP for it. We saw this in class that Denver and Mount Everest would have a lower boiling point to us because we're right about at sea level. Okay, section 3 and section 4, we have gases and phase diagrams that we're going to look at. Now we go a little bit lighter on gases because we're going to spend the whole next unit looking at gases for it. So, draw what gas particles would look like and give two properties of a gas according to kinetic molecular theory. So remember, we're going to have smaller spheres and we're going to draw them very far apart. So we're going to see that it has indefinite shape, meaning it takes the shape of whatever container it's in, and it has indefinite volume. That means it just takes the volume of whatever container you have. If you have a big container, it takes that shape. If you have a small container, it would be in that small volume for it. If you opened up the container, it would leave that container. We'll also see that they have rapid, meaning fast, random motion. There's no attraction to their fellow gas particles, so they're not bound like liquids or solids to feel their neighbor. And we'll see that they move in straight lines until there's a collision, and we call that collision an elastic collision. And what an elastic collision is that it's just going to hit and bounce, hit and bounce. Gas molecules are currently hitting you and bouncing off of you. So our final section, section number 4, we're going to use this phase diagram below. And we can see that our phase diagram has our 3 different colors, which represents our states of matter. We also see that we have pressure and ATM on our y-axis, so y going down, and our temperature on our x-axis. So what I like to do before I even read the questions is label everything I know about my phase diagram. So Y in the blue would be my solid, the green C would be my liquid, and the gray would be my gas or my vapor. Notice that CP, the critical point's already labeled, and we'll see this green spot right here is where all 3 colors meet or states of matter. So that would be my TP, aka my triple point for it. Now, since this is atmospheres, I can draw a dotted line going across, and that lets me know my standard pressure. Okay, so number 1, it says, what letter represents the solid region for the diagram below? Well, this one's on the side. So we notice that our solid's always closest to our Y, so that actually is Y for this. What state of matter would the substance be at blank ATM and blank degrees Celsius? So we're going to see that this just has to be at 10 ATM, and we're going to see at negative 100 degrees Celsius. So if we go for 10, we go for negative 100. We're going to pull it up, and we're going to see that it's in the green. That means that it would be a liquid. Okay, and what phase change occurs when you go from point blank to point blank? So for this one, we're looking for what phase change occurs when we go from C to A. So if we look, we have C here, and we're going to A. So C was an L, and we're going to a G, or gas vapor. So we would see that evaporation would occur. Sometimes you'll even see it as vaporization. And that takes us through the end of this assignment. Thanks for watching.